In this video, I will present Fundamentals of Causal Learning, an elective course that will be taught in Mastering Computer Science at the University of Luxembourg. As you probably know, data is the driving force for many modern businesses. For some of them, such as Google and Facebook, the analysis and collection of the data is the primary activity, while others use data to improve their services. The data is so important that sometimes it is referred to as the new black gold. However, as opposite to other black gold alternatives such as coffee and petrol, data has some interesting properties. That is, it is reusable, it is multi-purpose, and its value only grows with time. You already know that the amount of data is so big that it is impossible to analyze all of it by hand. That is why we use specialized algorithms that allow to identify connections between attributes that correspond to correlations between these attributes. However, correlations sometimes can be misleading. For example, let us consider two time series presented on this graph. Time series in red corresponds to the number of worldwide non-commercial space launches per year, while the time series in black shows the number of sociology doctorates awarded in US per year. We can see that the two time series follow each other very tightly. That will result in a high value of correlation. However, our common sense suggests that there should not be physical relationship between these two attributes. It means that automatically identified correlations can be misleading. So, is there something that can be done about this? Well, let us analyze an example. Assume that I have a data set as presented on this plot. We know that this data set was generated by a linear process. Additionally, we can assume that the noise is independent on the causal variable. That is a valid assumption in many practical applications. However, we don't know which variable is a cause and which variable is the effect. Is it y or is it x? If x is the cause and y is the effect, then our dataset should be explained by the first model, with ny standing for additive noise, and the corresponding regression line will look like this. However, if y is the cause and x is the effect, then the corresponding model will look like this, and the regression line will be represented by this orange line. So, is there any way for us to identify which line is correct and which one is wrong? Well, let us plot the residuals as a function of the causal variable. For the first model, we can see that there is no particular structure. However, it is not the case for the second model. Here we can clearly see a pattern that implies that there is a relationship between residuals or the noise and the causal variable that violates our previous assumption. That is why in this case we can conclude that y cannot be the cause, and the first model is correct. There are also other indicators that can help us identify the direction of the causal relationship. For example, simplicity assumption. For this particular data set, if we assume that y is the cause, then for a particular value of y, the causal variable will get different values of x, effect variable. That will make our model more complicated and thereby will violate the simplicity assumption. So, what will you learn if the next semester you take Fundamentals of Causal Learning course? First of all, we will discuss the conditions under which automatically identified correlations do imply causations. Next, we will discuss the experimental design to identify causal relationships. And finally, we will talk about how causal relationship can be identified not from the experimental data, but also from purely observational data. The course will be organized as a mix of lectures and practical tasks. At the end of the course, you will understand the limitation of causal inference and will get to know about the current trends in the new and very popular research direction, causal learning.